Hi, I'm Rohit, a student of Math 23A, presenting the paper with my classmates Michael Liotti, Robert King, and Zarek Mahmood. The paper we have implemented is written by a team at the Department of Applied Mathematics at the University of Washington and is called A Unified Framework for Sparse Relaxed Regularization Regression SR3. You can find the link for the paper in the notes that we provide, as well as in the R project GitHub location as well. Now, before we deep dive into the technical aspect of what the SR3 algorithm is, it is best to cover a few concepts like norm of a vector, the L1 norm that we will use for our function, the prox operator, and how to use the prox operator for L1 regularized optimization problems. Now, simply put, norm is a function that assigns a strictly positive length or size to each vector in a vector space. Compute the pth norm. We can define the equation for p is greater than 1. The pth norm of a vector x is equals to x1, x2 till xn as pth norm of vector x is equals to summation over xi raised to the power p and the pth root of the whole summation. Now for p is equals to 1, we compute the most basic norm called the L1 norm, which is the L1 norm of x is equals to the summation of the absolute values of all the components of x. Now the optimization problem given by the prox operator for the L1 norm can be written in the form of the equation argmin over argument x over argument mu, and the equation will be given half of u minus x whole square plus lambda into the L1 norm of mu, where argmin is the function that calculates the arguments in the domain of the given function where the function is minimized. Now to calculate the prox operator for this particular function, we can apply a trick which is as follows. We know that ui will be either positive, negative, or 0, and because it's a real function, and the derivative with respect to ui can be given in the form of ui minus xi plus lambda if ui is positive, and ui minus xi minus lambda if ui is negative. And for doing that, you just differentiate this equation with respect to u. And since we are minimizing the function, the derivative equals to 0 at the minima. So the equations that we derived earlier, when ui is greater than 0 at the minima, it becomes ui minus xi plus lambda is equals to 0, or we can write it as ui is equals to xi minus lambda. Similarly, and again, as ui is greater than 0, this quantity has to be positive, so we get xi is greater than lambda should always hold, or simply put, we can just concur that given ui is greater than 0 implies that xi minus lambda is greater than 0. This will be our equation 1. Again, similarly, if ui is less than 0 at the minima, our derivative will equals to 0, and our derivative was ui minus xi minus lambda. We equate it to 0, or we can write it as ui is equals to xi plus lambda. Again, ui is less than 0 should hold, so for that to hold, this quantity should be negative, and we can write it as xi is less than minus lambda should hold, or we can write ui is less than 0 implies that minus xi minus lambda is greater than 0. This will be our equation 2. Now the prox operator that we calculated here is reduced to the problem, and you can write it conveniently, and you can write a function out of it in R as combining, after combining equations 1 and 2, we get that the prox operator for the L1 norm of the function that we defined earlier is equals to sine of xi into maximum value of either mod xi minus lambda or 0. This is also called to be the soft thresholding, which will come further when Zarek discusses the code that he has written for implementing the SRC algorithm, and the soft threshold function will come as a function defined in his code.